and my end. Today, we are this is our week 13, and our agenda is design and analysis of beams with 3D mold circle. So this is the proper design work. Whatever you learn now is just a combination of what you have learned before for the past 12 weeks, and also from what you learned in 2P04. Okay, so if you cannot remember stuff from 2P04, I will strongly recommend that you do. So the topic we're going to do is design analysis of beams. And I think that in the lecture on Wednesday, there's this diagram that I post. If you can go to this diagram, you'll be fantastic. Okay, so I'm going to take these images. Right. So the structure that we're going to analyze, so this is the first example, this is the example we're going to do. Okay. So the structure that we use for this question is W250 28.4. Okay. So so we're going to use W250 by 28.4. Okay. So if you were to look at the cross section, but before I go on, we know that this structure, okay, so the structure is under both shear force and bending moment loading. Okay, we are aware of that, right? So the question is now, if we look at the cross section, right? We look at the cross section. If we were to just look at this cross section, and if we're going to sketch the shear stress is equal to VQ over IT. And for this case, we are going to do thin wall analysis. Right? We realize that our structure, this is just a sketch, by the way. Okay, so this is shear stress. This is our Y. Okay, and because it's thin wall analysis, we were going to get a distribution like this. Okay, so this is based on thin wall. If it's non-thin wall, it's going to look like this. It's not bigger or higher. So this is based on non-thin wall. Okay. So what we realize is that over here is where tau max, right? And we also are aware that the loading is also induced by bending moment. Okay. And I have to shift this slightly. So this is normal stress. This is your Y. And we are going to get a distribution looking like this. Okay, we're going to have a distribution looking like this. For example, this is just an example. Okay, we're going to have a distribution looking like this. And we realize that over here, this is where, right, at this position, this is where we get our stress mean, or we get our what? Stress max. Okay. And at the centroid, our normal stress is equal to 0. So in the cross section, okay, where will failure occur, right? So will failure occur at point I? The thing about point I is where you have stress max and the shear stress is equal to what? 0, right? If you look at the distribution. The thing about the centroid is where you have stress, normal stress is equal to 0, you get your shear maximum, right? So where it will fail here. So failure will occur at the intersection between the flange and where? And where? Are we clear? Failure will occur in the intersection between the flange and web. Can someone tell me why? It does not have the highest normal stress, neither does it have the highest shearing stress, but why failure will occur there? Anyone, please? Anyone? Yes. So what is going on at the transition area? You're right, it's a transition area. What's going on at the transition area? You're right. Yes. So what happened when thickness jump? You're partly right. So over here, if I zoom closer, can you see this radius over here? Come on. You have a what? You have a radius down here, right? R. And the R value, the smaller the R value, the higher the stress concentration factor. Are we clear? Right? The smaller the R value, the higher the stress concentration factor. And this stress concentration factor will be taught in 3EO3. I don't teach you here. That's the difference. So when you order a beam like this, you have to know the what? The beam. The smaller the radius, the higher the stress concentration factor is usually a multiplier greater than what? Greater than 1. Okay, and all these are available by a graph. Okay, by looking at a graph, this is your radius, this is your stress concentration factor. Nothing difficult at all. The difficult part is this. Okay, what we are doing. So we are aware that failure will occur at point where? At R. Yes, or at the intersection between the what? Between the flange and the what? And the web. That's where failure will occur. The next question is this. If you look at if I were to call this okay, is Y, and this is our rotation X. Okay. The next question comes, where about along the beam failure will occur? Yes. Oh, rotation above Z. Thank you. Okay. Now, on the beam, right? The next thing we ask yourself or ourselves, where failure will occur. You can see there are two different scales, yes or no? Right? Over here is the longitudinal. Over here is the what? The cross what? The cross section. We know where the cross section will fail. We know the cross section will fail where? At the cross section, we know this point. We know specifically where the cross section will fail. But along the beam, where it will fail, we don't know. Okay, this is where things get interesting. Okay, this is where you combine whatever we learned in 2P, 3A, and later on 3E to fully design a beam like this. Okay, so if you were to ask me, can you design a beam like this? Yeah, we have 90% of the knowledge. The only knowledge we don't have is the what? Is the stress concentration factor. That's the only thing that we don't have for now. Okay. So now let's look at the longitudinal direction and see where failure will occur. Okay, so I'm going to copy this. Any one question so far? Are we okay? We're good. It's interesting. When I look at you guys on Monday, it's the same 80 people in this class. Okay. Any idea how many people failed term test 2? Anyone want to make a guess? The other 80 people that don't show up, this class is 160. Okay. It is interesting observation. Okay. So by fate, I believe you all pass. Okay. Really, I do. Longitudinal analysis. Okay. So the longitudinal analysis is not difficult to do at all. Okay. So what we're going to do, we are going to sketch. Okay. I'm going to draw this side. We are going to sketch and label the shear force and bending moment diagram. Right? We're going to see it. So before we do that, we have to determine the reactions at point B and point D. Okay. So to draw this, we know that we have a force over here. Whenever there's a support, we have a By, and there's another support over here. This is our what? Our Dy. Okay. So what we are going to do, we are going to carry out static analysis. So this is what you all learn in 2P. So we are going to take summation about moment about on the z-axis at point D, and everything is equal to 0. So now if I was to sketch our transformation, this is just a very quick recall for you. This is our x, and this is our y, and over here, this is our rotation about z. Okay. So first of all, we have to determine our equivalent load on the distributed load. So this is our equivalent